Hello everyone, my name is Ji Xuanzhi. I come from George Mason University. Today I will present our work, Designing Human-Robot Coexistence Space. Let me start by introducing the idea of human-robot coexistence space. Robots are designed and developed to work with and around humans. Humans and robots will share a common space. A better designed space shared by human and robot can enhance human-robot interaction and collaboration. We propose an optimization framework to generate layouts that consider both human preference and robots' constraints. The left part of the figure is a worse layout design compared to the right part, which is produced by the proposed framework that considers human preference and ensures that all the objects are accessible by the robot. There are two major topics related to this paper: computational design of space planning and motion planning in similar environments. Computational design of space is usually formulated as an optimization problem. They consider user-defined rules and human activities for object placement. Motion planning methods that use previous experiments to solve new problems. The previous experiments include the representation of the workspace and the recorded trajectories. This figure shows the overview of the proposed method. Given the room size and objects with the user-defined action-object relation graph and the input, our approach generates scenes and paths by the optimization and the motion planner. This space layout and paths are evaluated until satisfy the human preference and the wheelchair motion constraints. We will describe the details of these components in the following slides. Firstly, let's see the layout design input. The figure on the left shows the room and the different objects here. For objects, we consider spatial relationship, including distance and orientation between two objects. Those relations will be used in the optimization part. Then we need to talk about the path design input, action-object relation graph. In a given room, objects inside the room play an important role in defining the activities of humans and robots. These activities define how humans and robots may move around the room. An action-object relation graph reveals the activity associated objects relations. This is a weighted directed graph. The node represents the objects. The edge width measures how likely a wheelchair robot may move from one object to another. The figure on the left shows the action-object relation graph in a bedroom. Edge thickness represents the transition probability between two objects. Let's talk about how to define the paths in a room. Given a sequence of objects that wheelchair should visit, we need to find a path that allows the robot to stop by each object. In other words, we need to find a sequence of configurations, one for each object. So the path connecting configurations in the sequence is collision-free. These configurations should be sampled around the objects and should be oriented so that the person sitting in the wheelchair is facing the object. The figure on the left shows an example of the sampled configurations around the bed. We need to find a collision-free path that visits all the objects in the sequence that satisfy the no-holonomic constraints. We use a branch and bound approach to find the path. All pairs of configurations are sorted based on their redshift curve lengths. Starting from the closest pair, the pairs are iteratively evaluated by the motion planner until a valid path is found. The figure on the right shows an example of a path between the bed and the TV. After generating the layout and path, we need to evaluate and do an optimization. We define cost terms, path cost and interior design cost. Path cost include length cost, rotation cost, clearance cost. Interior design cost include pairwise distance cost, pairwise rotation cost. In this paper, we apply a simulate a nearly method with a metro policy hosting algorithm. First, we define an objective function for the state, T is the temperature here. The proposed method create a realistic layout and path by minimizing the cost here. In each iteration, our method choose a mode to change the present configuration P and I to a new configuration P prime and I prime. The new proposed configuration is accepted with a probability based on metro policy criteria. In the beginning of each iteration, the optimizer may accept any move when the temperature is high. As the temperature decreases, the optimizer is less likely to accept a bad move. For more details, please refer to the paper. Then let's talk about the motion planning part. We construct a wheelchair motion planner. It models a wheelchair as a non-polynomial core. The planner uses a variant of rapidly exploring random trains with the reed-shaped curves. The key technique challenging is to overcome the bottleneck result from the repeated calls to the motion planner during the optimization process. As shown in our experiments, motion planning takes more than 95% of the computational time. We propose an ultra-fast non-polynomial motion planner that reused and adopts early solutions. The first method that we use is to decompose configuration space with reed-shaped words. We uniformly sampled configurations around the room, compute the shortest reed-shaped curve from the center to those configurations, and store the RS word. During the motion planning part, when calculating a new configuration point, we find the closest sampled points with the KD tree structure and retrieve the word and compute the path directly. The figure shows the resulting partition of the configuration space into 48 regions. Secondly, we talk about how to reuse the computations. As the optimization converges, the layout design stabilized. Therefore, it is in fact possible that we can reuse the early solutions. We can reuse the path within the optimization iteration, construct a database to store the trajectories between pair objects. Then we can reuse the trajectories whenever it is possible. In addition, we can also reuse the path from the early optimization iterations. We look up the database built from the earlier iterations and extract a potential path for the new layout. Then we can transform the path to the new location and orientation. Similar, we can reuse the RT tree. If the position of the RT route does not change much, we can reuse the tree from the previous optimization iteration. Then let's see the experiments and the results. We test our framework in 3 different scenarios: bedroom, office room, and living room. The figure shows one layout design, the path covering 3 different objects in each scenarios. In all 3 examples, the wheelchair starts from the door. The video shows an optimization process of an office room use our proposed motion planner here. And then we show a first-person view that illustrates how a human in a wheelchair can easily navigate in the space. Finally, we show that an evolution of the optimization cost over time. Then we compare the average path planning time in 3 different environments with 2 different planners. As shown in the results, the proposed planner significantly outperforms the baseline planner in all cases. The proposed method reduced the planning term between 65% to 17%. We further evaluate the proposed method in a room with more complex boundaries, such as L-shaped room. The figure shows two desires generated for the L-shaped living room. Both layouts satisfy the layout and path requirements. Because our method also considers the human preference, and those human preferences are encoded in cost weights. To illustrate the effect of those weights in the resulting designs, we select two different path cost weights here. Figure on the left use weights which only care about the path rotation, and the figure on the right use the weights which only care about the path length. This figure shows the two layout design from those two different path cost weights. Regardless of the weights, the path must cover door, round table, office table, sculpture, and bookcase. The results show that path in the left design has longer length and fewer turns, and the path in the right design has shorter path length and many turns. Those results reflect the provided human preference. In this work, we propose the first node optimization framework for designing human-robot shared space by considering human preference and robot constraints. We also provide a normal non-harmonic motion planner that can efficiently solve motion planning problems in many similar workspaces. The experiments showed that our framework can generate reasonable layout design, and the proposed motion planner takes significantly less time than the baseline planner. There are several limitations in this work. For example, the number and type of objects in the rooms are really small. Thanks for your attention. Please visit our website for more information. Thank you.